Okay, we're back in Module 8 on interval estimation, but now we're going to take up the last part of this module called determining the sample size, which will be a little bit different than what we did in the earlier portions. Throughout our modules so far, we've usually given you the sample size on any problems that we did. And in many cases, if a researcher is using existing bodies of data, the sample size will already be determined for them. If I'm using data from the Labor Department or the Census Bureau, somebody else already took that sample, and I will simply be using whatever sample size they have. However, there are many situations where researchers gather their own data, and the researcher has to choose the sample size that they want to take. And while it's always desirable to have a larger sample size, it's also more costly to have a larger sample size. It takes time and effort to gather data, so there's a trade-off there between the size of the sample and the cost. Let's go back to our first confidence interval for mean. Suppose your ultimate goal is to estimate the mean of a population. Remember, our first formula was this one right here, x bar plus or minus z sigma over the square root of n. Remember, everything to the right of the plus or minus is what we call the margin of error. So the margin of error, which I'm going to call E now, is equal to z sigma over the square root of n. Notice that equation has four parts to it: E, the z value, sigma, and n. Just take that equation and solve mathematically for n, the sample size. You don't have to worry about the math, but if you like to do the equation, you'll have to multiply both sides here by the square root of n to get that out of the denominator, square it to get rid of the square root sign, and divide the e over to the right-hand side. When you do that, you will get the following formula. N is equal to the z value squared times sigma squared over e squared. What that formula is showing you is that the sample size we need depends on three factors. What's the level of confidence I want, which determines the z value? What's the variance of the population, sigma squared? And what margin of error, E, do I want? Remember, the margin of error is just how close to the true population mean do you want to come. The researcher basically can control for the first and third items here. You can choose the level of confidence you want, which determines the z value. You can choose the margin of error you want. We have a slight problem, however, with number 2. We need the variance of the population. You might not know that, but you're going to need some prior estimate or some past estimate of the variance of the population. So let's assume that you can do that. Then all we have to do is plug everything into the formula. Let's do an example. Suppose you were going to take a sample of Triton College students in order to estimate the average age of the student body. You desire to estimate the average age to within 1 year of the actual mean. So that's your margin of error. You don't want to be off by more than 1 year. Past data indicate the standard deviation of ages of Triton students to be 4 years. So you're given a standard deviation figure. At 95% confidence, how large a sample would you need to take? And 95% confidence, as we know, implies a z-value of 1.96. So now we can just plug everything into our formula. N is equal to the correct z-value squared, sigma squared over e squared. That gives us 1.96 squared times 4 squared over 1 squared. If you work that out, you will get a sample size of 61.46. Of course, you can't take a sample of 61.46 people, so we're going to round that up to the next largest integer, 62. We would need to take a sample of 62 students in order to estimate the population mean to within 1 year with 95% confidence, assuming the standard deviation to be 4 years. Notice a little technical point. We always round up sample size problems. If you get a fraction, round it to the next largest number, the next larger number. Do not round it down. And the reason for that is If you want a certain level of confidence and you want no more than a certain margin of error, then the prudent thing to do is round up that fraction. If you round it down, you might not have as much confidence as you thought. If you don't remember where the z-values of 1.96 came from, I've just repeated a chart that we've looked at before. Remember, the level of confidence is called 1 minus alpha. That's in the middle of the distribution with an alpha over 2 probability in each end. Find the z-values that do that, and you should be able to find that they're plus or minus 1.96. Let's do another example, the same formula. A consumer research organization periodically estimates mean gas prices in a large city. Suppose they desire 99% confidence in their estimate and a margin of error of 0.04. Assume the population standard deviation is known to be 0.15, which would be 15 cents basically in gas prices, but we'll leave it in decimals as 0.15. How large of a sample would they need to take? Once again, just going through the problem, you want 99% confidence, which you should recall implies a z-value of 2.575. We want the population standard deviation is known to be 0.15, and we'll square that figure. And we want a margin of error of 0.04 in the denominator there, and we will square that figure. So we have the following calculation: 2.575 squared times 0.15 squared over 0.04 squared. And if you work that out, you will get n to be 93.23. Rounding it up to 94, we need a sample of 94 gas prices in order to estimate the mean gas price to within 0.04 of the actual mean, assuming a standard deviation of 0.15 and 99% level confidence. Okay, now we're going to do the exact same thing, except suppose you're going to estimate a population proportion and not a population mean. So once again, we want to talk about predetermining the sample size before you've actually done your estimate, before you've gone out and calculated a confidence interval. Again, let's go back to our formula for a confidence interval for a proportion. P bar plus or minus z times the square root of p bar times 1 minus p bar over n. Everything to the right of the plus or minus is what we call the margin of error, E. So we have E is equal to Z times the square root of P bar times 1 minus P bar over N. And once again, we're just going to take that equation and solve for N. If you solve for N, you're going to get the following formula. And again, you don't have to worry about the algebra. N is equal to, again, the Z value squared times P bar times 1 minus P bar over E squared. Now, first problem we have is P bar. Since we haven't taken a sample yet, because we're asking ourselves how large a sample size to take, we don't have a sample proportion yet. So instead of calling this P bar, for right now I'm going to call it P star. I'm going to change it to P star. Same formula, except we've changed P bar to P star. So we have the formula N is equal to Z squared, P star times 1 minus P star over E squared. Now again, if we take a look at the parts here, our sample size depends on 3 factors. What's the level of confidence you want, because that determines the z-value. What's the margin of error in the denominator? Well, we can choose that. And lastly, P star. And as I've already kind of implied here, the researcher has control over the first 2 things here, 1 and 2, but we have to do something about P star. The researcher can choose the level of confidence they want. They can choose the margin of error. That is, how close to the true proportion do you want to come. What about P star? There's 2 possibilities. You can use what is sometimes called a planning value, maybe from another study. Maybe somebody else has done similar research as to what you're doing, and there might be an estimate of the population proportion around. If so, go ahead and use it. If you have no other possible value for p, then the conservative thing to do is use p star to be a half. Assume it's 0.5. Why is that the most conservative thing to do? Well, if you look at the formula here in the numerator, we're going to be multiplying p star times 1 minus p star. If we assume p star to be a half, you'll have a half times a half, which is a fourth. You can prove in mathematics that for two numbers that add up to 1, a half times a half gives you the greatest value that multiplies to, namely a fourth, as compared to any other two values. 0.6 times 0.4, for example, would be 0.24. 0.8 times 0.2 would be 0.16. All of those would be smaller than a half times a half. So that'll give you, since p star is in the numerator, that'll give you the largest possible sample size. So that's why we call it the conservative thing to do. Let's do a problem. As part of a class project, a group of students want to estimate the proportion of students who drive to campus as opposed to other forms of transportation. They hope to estimate the proportion with a margin of error of no more than 5%, or 0.05, with 99% confidence. How large a sample should they take? So we want the margin of error to be no more than 0.05, so that's E. 99% confidence, you might recall, gives us a z-value of 2.575. Nothing in the problem gave us a prior value for p, so we'll initially just use 0.5. Plug everything in our formula. N is equal to the z-value squared times a half over 0.05 squared. If you work that out, you should get a sample size of 663.06. Round that up to 664. So we would need a sample of 664 students if we wanted to estimate the proportion of students who drive to campus with 99% confidence and a margin of error of 0.05, assuming that the population proportion is 0.5. Again, in case you don't remember the z-values for 99% confidence, I've just drawn a little graph here to remind you of those. 0.99 in the middle of the distribution, meaning 1/2 of 1% in each end, 0.005. Go to your z-table and you should be able to find those values to be about 2.575. Let's do a second example, but actually just a continuation of the one we just did. Let's do the same problem, except this time assume that we do have a prior estimate of p. Suppose a previous study had estimated that 75% of the students drive to school. So we're now going to use 0.75 as our value of p. Plug everything in the formula now. 2.575 squared times 0.75 times 0.25 over 0.05 squared. And you will get a sample size of 497.28. Round that up to 498. So now we would only have to take a sample of 498 students in order to estimate the proportion of students who drive to campus with 99% confidence and a margin of error of 0.05, assuming a proportion of 0.75 is our planning value. Notice that having that planning value, having that prior estimate, reduced the necessary sample size quite significantly. When we had no such prior estimate, we had to take a sample of 664. But with this prior estimate, we only need a sample size of 498. And that's the end of Module 8. And in Module 9, instead of estimating things, we're going to start talking about testing hypotheses.